Hello, this is Dr. Lori. Welcome to this discussion on standardization. As a little background, by now you've probably realized that epidemiologists and biostatisticians like to do a lot of comparing. Well, sometimes when we'd like to compare two things, there are nuisance factors, factors that are garbling up the relationship that we're really trying to look at. So in this example, we are going to be looking at the nuisance factor of age. Now, it's very common for different counties or countries or cities or towns to have a different distribution of a particular factor, and age is one of the common ones. So, especially because we can't really do any interventions on chronologic age. We can't say, okay, well, I'd like for you to try really, really hard and lose 10 years of age. We just can't do that, and so we're stuck with our age. We are the age that we are, and so we're not going to be doing interventions to try to get people to be younger. So it's not a modifiable risk factor. The other kinds of things that often we will standardize on are things like gender, to make populations more similar in terms of gender. We might standardize on race ethnicity if that's not the factor that we're interested in looking at. We might standardize on socioeconomic status. There are all kinds of things we might standardize on, but I would say that in the literature, the one that you will probably see the most is age standardized. And so very often at the bottom of the table it'll say that the values are standardized for age, or they're age standardized. So that's what we're going to be doing today. So I'll walk you through this. Don't get blinded by the numbers. Just kind of take a general look at them and I'll walk you through what all of these mean. What we're going to do today is we're going to be looking at 3 counties. We'll just imagine that they're all in the same state. We could pretend that they're all in California, although then I don't think the numbers match any counties that we actually have. So we'll call these 3 counties Young County, Mid County, and Old County. And the reason that we've named them these is that the population in that particular county tends to be a little bit younger than average, pretty close to the average for that particular state, and a little bit older than the average for that state. And so what you see here on the left-hand side then are the different age brackets. This first row here is for all of the under 5, so anywhere from birth to age 4, all the way until their 5th birthday. This next row starts when they're 5 and ends all the way when they're 14. The row after that starts at 15 and goes to age 49. Then we have the 50 to 69-year-olds, and then finally the 70 and older. Now, an important thing to remember about any kind of standardization is that within whatever stratum that you choose, it's beneficial if the risk that occurs through that stratum is pretty similar. The whole reason that we choose different age groups or different other groups is that we think that it's a pretty homogeneous group. So in this example, age 15 to 49 is pretty wide. If you look on the GBD Compare, that's one of the age categories that they choose, so that's why we used it for this example. But if for a particular outcome there's a lot of difference, say between 15 to 30-year-old, 29-year-olds, and then 30 to 49-year-olds, then you'd probably want to split this in half so that each one of those groups that's different from each other can have its own stratum. And it'll make more sense why once we get farther along through here. So what we've done is we've taken, let's say, a particular year. We can guess that this is maybe 2016 or some other recent year. And for Young County, we have collected some information of that for that particular location for that particular time on incidents. Now, if you remember, incidents is new cases divided by population at risk, and both the numerator and the denominator are counts. If you're looking at incidents, the numerator is part of the denominator. In other words, that population at risk, that's where the incident deaths came from. Now, we don't usually say incident deaths. We usually just say deaths or mortality. But I put that in there because I wanted to make sure that you knew that these were incident cases. They are new cases. And so that you could conceptually in your mind replace deaths with anything else. Incident diabetes, incident heart attacks, and then you would just simply replace that word in the other columns as well. So you could replace that with disease, so then it would be incident disease. So these are incident cases, and so the way we would read this is that in the under 5 age group, there were 3 deaths during that time frame in that location out of a total 7,500 population at risk. And when we're talking about deaths, we generally consider the entire population at risk for death. So mortality is kind of an easy example to have in this case. Then for the 5 to 14-year-olds, there were 4 deaths, and the total population at risk for that age category was 20,000. Similarly, for the 15 to 49s, we had 27 deaths out of 45,000 at risk. For the 50 to 69-year-olds, we had 115 deaths out of 25,000 at risk. And for the 75 plus, we had 80 deaths out of 2,500 at risk. So the totals here are 229. I've set up the example so that the total population at risk is equal to 100,000. That makes it easy for us just conceptually to see that the crude death rate is 229 per 100,000. So we have this 229 per 100,000. Now what if the population at risk wasn't exactly 100,000? Well, we'd probably want to multiply all of these out so that we could use the per 100,000 as our factor. And so the way we do that is we take the deaths, which for this age category is 3, divide it by 7,500, and then multiply both the top and the bottom by 100,000. And what we get is we end up with the number 40. So 40 per 100,000. So what this does is it allows us to compare, even though the size of the groups is different, we can see relative to at least each other which group seems to be at greatest risk. So these first 2 were counts, but as soon as we take and divide incident deaths divided by the population at risk, now we have a proportion. So we have the risk or incidence of death. Remember, incidence and risk of death are kind of interchangeable. We repeat that same process for each of the rows. So 4 per 20,000 is equal to 20 per 100,000. 27 per 45 is equal to 60 per 100,000 deaths. 115 out of 2,500 is equal to 460 per 100,000, and 80 divided by 2,500 is equal to 3,200 per 100,000. So now we have the risk of death per each of the categories, and then we need to multiply that by the percent for that particular county. Now, since this is 100,000, it makes those percentages sort of logical. We have 7,500 per 100,000. That's 7.5% of the county. So this is specific to Young County. Here we have 20% of the county is age 5 to 14. 45% of the county is age 15 to 49. 25% of the county is age 50 to 69, and 2.5% of the county is age 70 plus. So because we set the denominator at 100,000, that just makes these intuitive, but they would not be if this number weren't 100,000, and it would be pretty unlikely to find multiple populations that are exactly 100,000. So it's worth going through the calculations. This, of course, should add up to 100%. And then we take that risk of death times the percent to end up with the crude incidence. And so 40 per 100,000 times 7.5% is equal to 3 per 100,000. So remember, these are now all per 100,000. If we add all these numbers up, we end up with 229 per 100,000, which is exactly what we got when we were just looking at the raw numbers, and we had this magical county that just happened to be a perfect 100,000 in the denominator. So this really confirms what we did over here. Again, we wouldn't need to do this if we had a county that had exactly 100,000 in it, but since that's rarely the case, then we multiply this out to get our crude incidence of death. Now, we repeat that exact same thing with Mid-County right here and Old County, and you'll notice that the incident deaths are slightly different. For Mid-County, they had 2 deaths instead of 3 in the under 5s. They had 3 deaths instead of 4 in the 5 to 14s. They still had 27 deaths in the 15 to 49s, so that's exactly the same. But they had more deaths in the 50 to 69s and quite a few more in the 70 plus. So their total number, even though these numbers were smaller, these numbers were quite a bit bigger. The crude, the total count went up from 229 to 330. So 101 more total deaths in Mid-County. So you'd think, wow, Mid-County must have a higher mortality rate. And they actually do. When you go through that whole same process that we just did, they have, for their crude mortality mortality risk, they have 330 per 100,000. So Mid-County has a higher risk of death than Young County. And if you look at Old County, their incident deaths for the under 5s is even lower. The 5 to 14s again is lower, but the 50 to 69-year-olds and especially the 70 plus is quite a bit higher. So the total incident deaths is 431. They also have a population that adds up to 100,000. So their risk of death is 431 per 100,000. So these are all percentages for the county again, and that comes from the number in that particular age category divided by the total. And so these are the crude incidents. Now we're going to do a magic trick. You probably saw this down here. I'm going to go ahead and bring it on up. There we go. You're going to have to imagine the Mid-County right there, just because we need the room. What happens with standardization is that we do that same exact process. as coming up with the crude mortality, except that instead of using the local populations, we replace those with a standard population. So let's take a look at that standard population here for a minute. Let's just say instead of using young, mid, or old county as our standard population, we want to look maybe at the state overall. Maybe these come from the state of Whoville or someplace. So here we have the state overall, and the state has 5% of its population is under 5, 15% of its population is age 5 to 14, 45% of its population is age 15 to 49, 30% of its population is age 50 to 69, and 5% of the population is 70 plus. So this is kind of a nice middle of the road population. It's not particularly young, it's not particularly old. And we go through that same exact process where we look at the incident deaths, the population at risk, and then we take 3 divided by 7,500, multiply by 100,000 on the numerator and the denominator, so we end up with 40 per 100,000. That's our risk of death. And we do that then for each of these rows, and because these numbers are exactly the same as what we've already done, then we will get exactly those same numbers. The difference lies in that what we multiply that times to get the contribution to a standardized incidence instead of a crude incidence. We multiply that risk times the percent of the standard population. So instead of multiplying 40 times 7.5 to get 3, we multiply 40 times 5% to get 2. And so now we are removing the effect that age might have that's kind of muddying up the waters to be able to compare young county to mid county to old county. So let's go ahead and take a look at the numbers that then were produced. So we basically took these percentages from the standard population, whatever we're calling that standard population. It can be any realistic standard population, and copying those right in here and multiplying those out. And when we do that, an interesting thing happens. Instead of the crude rate that we got from before, 229 per 100,000, which is right here, we add those up and we get 330 per 100,000. And so what happens to a young population when you age standardize is that the mortality rate goes up. Now that is not automatically intuitive. If you were to think about it without going through the numbers, you might think that it's the opposite direction, but here's one way of thinking about it. Basically, compared to the standard population, we were missing a bunch of people down here in our high-risk group. Let me go ahead and highlight that maybe in gray. We were missing people who had a high risk of death. And so by inserting this standard population, we basically put those people back. And so instead of having just the 80 deaths that we did have out of the 2,500, we replaced that population with 5% of the population, and we ended up with the 160 that would have been there if the population had been older. And so when you take a young population and age standardize it, if the older people are at higher risk, then what that means is it adds back the risk for those older people. And this 229 crude per 100,000 mortality increases to 330 per 100,000. Now in mid-county, the interesting thing is the percentages for the county itself and for the state are actually identical. So we happened to have a population, have a subpopulation that's exactly the same as our standard population. And as you would probably intuitively guess, this age crude mortality is exactly the same as the calculated standardized mortality, age standardized mortality. So if you're multiplying by the same exact factors, be it crude or standardized, then there is no change in the value that you get for the risk of death, for the mortality risk. Now here's Old County, and basically we have extra people in this high-risk group. And so when we apply the standard population percentages, a number of incident deaths, or the count, to 40 actually goes down because we had more people in that group than would have been there if we did have a standard population. And so what this does is it removes those extra deaths that were just because we have a bigger population there. We have a larger population in that high-risk group. And so when we age standardize the mortality in this particular situation, our crude was higher than the age standardized mortality ended up being. So when you have an old county or an old country or an old town, and you age standardize to the standard population, getting rid of that high risk group, then your risk of mortality, the risk of death, goes down. So I hope just going through that whole process has helped you see what standardization can do. In summary, if we were to try to compare Young County to Mid County, if we were comparing just the age crude, we would say, oh, it looks like Mid County has a higher risk of death. But that higher risk of death is only because they are older. Their age distribution is older. Another takeaway message from this is that a lot of times we think about countries, Western Europe, North America, tend to have an older age distribution than the average for the whole globe, for the whole world. And it's not entirely intuitive that countries with an older age distribution also inherently have a higher mortality rate. You would think, oh, well, they have better health, better access to health services, they tend to live longer, therefore their mortality must be lower. And actually, it's not. And the reason for that is this whole idea of denominators. If you work through that several different times and think about the reasons for that, then what that does is it shows that we have disproportionately higher numbers in this high-risk group, and so then what that does is it pushes the crude mortality up. But then if we were to take countries who have a population that tends to be older and age standardize them, then what that does is it removes that artificial effect of just being older, and then we can compare between countries a little bit more equally to be able to see the effect of some other factor that maybe we could have an impact on, or we could influence. So removing the effect of age by standardization is a common practice, and it can help you so that you can compare between two locations. Thank you for joining me for this video.